Hello students, my name is Shubham and I am your physics faculty at Midha Guru, and today we are going to read a very interesting chapter, that is radioactivity. It comes under modern physics, and in this chapter we will first understand atomic structure. Then we will talk about different types of isotopes, isobars and isotones. Then we will understand the radioactive emissions. In case of radioactive emissions, there are two scientists worth noting here. These are Ernest Rutherford and Henry Becquerel. We will then move forward and understand the different components of these radioactive emissions, that is alpha emission, beta emission and gamma emission, and then we will conclude our discussion with their harmful effects. So let us start now. So first we will understand the structure of atom. In fact, if I talk about the size of atom, then the size of atom is of the order of 10 to the power minus 10 meter. It is very small if we compare it even with 1 millimeter. Atom consists of three main subatomic particles, and these are electron, proton and neutron. Now electron has a very negligible mass, in fact, when compared to proton and neutron, and the mass is 9.1 into 10 to the power minus 31 kg. Its charge is, however, minus 1.6 into 10 to the power minus 19 coulomb. Now this minus sign actually that you are seeing here actually denotes that it is negative charge. For proton, the charge is same but without this negative sign. Next we have proton. The mass of proton is 1.6726 into 10 to the power minus 27 kg. So you can see here, if we just compare this 10 to the power minus 31 and 10 to the power minus 27, then you can say that it is somewhere around 10,000 times more heavier than electron. So naturally, when we are considering the mass of an atom, we do not consider the mass of electron. It is assumed to be negligible. And if we talk about the charge, however, then the charge on a proton is same if the quantity, the magnitude of charge is same as that of electron, but with an opposite symbol. For electron it is minus 1.6 into 10 to the power minus 19 coulomb, and for proton it is plus 1.6 into 10 to the power minus 19 coulomb. Next we have neutron. If we talk about the mass of neutron, it is very close to the mass of proton. As you can see, up to 2 decimal places, the mass of proton and the mass of neutron is same. However, in the third and fourth decimal place, there is very slight difference. And in most cases, when we are talking about the mass of proton and neutron, we take them approximately equal. Now, when we talk about the charge of neutron, then literally neutron is neutral and it has no charge. And that is the reason that neutron was discovered much later compared to electron and proton discovery. Now, let us see the structure of atom. If I talk about the structure, then you can see at the center is the nucleus. Now this nucleus comprises of neutron and proton. And collectively, since these neutrons and protons are collectively forming the nucleus of an atom, hence these two are also called nucleons because they constitute the nucleus. And in other words, you can say that they form the nucleus. That is why neutrons and protons together are called nucleus. And these nucleons are actually responsible for the mass of an atom. As I stated in the previous slide, the mass of electron is almost negligible compared to proton and neutron. That is why we do not consider the mass of electron while calculating the mass of an atom. Now if we talk about the electrons, then you can see that electrons are arranged in certain circular orbits. And in fact, this model was given by Niels Bohr, and this model is also called, and hence called, I would say, Bohr's model of atom. Now here we have certain orbits. Now you see, it was Rutherford who first mentioned that electrons are arranged in circular orbits. But the mistake that he made was that he said, similar to the way in which we have our solar system, like the sun is in the center and planets revolve around it in circular paths, which is again not correct, absolutely true, because we know that the orbit is elliptical. However, even if that is the case, then we know that there is gravitational force which keep planets in their respective orbits. He was unable to explain what is responsible to keep these electrons in the circular orbit, because if anything is moving in a circular orbit, with time it will lose energy and ultimately these electrons would have collided into the nucleus. This was something which Rutherford was unable to explain. Later on, Niels Bohr took upon this task and he explained that there are certain orbits which are called shells. Okay, and the energy of these orbits are fixed. So if I talk about the first orbit, then the energy of first orbit will be fixed, and no matter which electrons are here. Like here we have 2 electrons. Of course, we know that using the 2n square formula that in the first orbit we will have maximum of 2 electrons. So if there are 2 electrons, then the energy of these 2 electrons will remain fixed if they remain in this circular orbit. If I want to remove one electron from this orbit and let's say I want to switch it into the second orbit, then I'll have to supply energy so that the energy of this electron increases, and then it will jump from first orbit to the next orbit. Again, if I want that an electron from a higher orbit should come into a lower orbit, then I need to ensure that the energy from this electron has been taken away. Okay, now by giving this theory that the energy of an orbit is fixed, he was able to justify that why electrons will move around the nucleus in circular orbits. And since the energy of these orbits are fixed, these orbits are also called stationary orbits. Okay, so now let us move forward. Now you see, the protons and neutrons form the nucleus and are together called the nucleons. As I mentioned earlier, each shell has definite energy, and the number of these shells in an atom depends on the number of electrons in it. Now this point is important. So let us say, if I talk about the Bohr's model of atom, then we all know that the formula is 2n square to find out the number of atoms, the maximum number of atoms that we can accommodate in a given orbit or shell. Now if we are talking about first orbit, which is also called K shell, then we know that the number of electrons that can be adjusted, the maximum number of electrons is 2. For second orbit, that is L, the maximum number of electrons is 8. For third, it is 18, and we can derive so on for other orbits. Now, these are the maximum number of electrons. There is one more rule which governs the filling of electrons in these orbitals, and that is called the octet rule. With one exception, especially for lower elements, lighter elements, where you can have duplet in the outermost cell. The octet rule actually states that the maximum number of electrons that can be accommodated in the outermost shell, outermost orbit of an atom is 8. Or 2 in case of some lighter elements like hydrogen, helium, lithium and beryllium. Also, I think boron. Now, based on that, if I say that there are, let's say an atom has 10 electrons, for example. So what will be the atomic structure? How I will distribute the electrons and how many number of orbits will be there? So I know by for sure that in the first orbital, I can accommodate a maximum of 2 electrons. Then I am left with 8 electrons. So these 8 electrons can go directly into the second cell, which has a maximum capacity of 8 electrons. Now you see here that this does not violate the octet rule as well. This is the outermost shell and it contains a maximum of 8 electrons. Okay, so I need for an atom which has 10 electrons, there will be 2 orbitals in the atom. First will be K and second will be L. Now, the third statement says that each shell has a limit on the number of electrons that can be filled in it. It is given by 2n square, where n is the shell number, which I have already explained. So now let us move forward. Sorry. Next, let's talk about chemical and nuclear change. If I'm talking about a chemical change, then a chemical change occurs when there is a transfer of electrons. That is, it is an orbital phenomena, and the energy required for transfer of electrons is much less. Although it is high compared to some physical phenomena, but it is still lower when we compare it with another kind of you can say change which is nuclear in nature. But when it comes to nuclear change, then in this case what happens, the number of nucleons change actually. However, there is one catch here. In case of a chemical reaction, we say that the total mass of the reactant is equal to the total mass of the product. In case of nuclear reaction, what actually happens is that the atoms might change. Like initially you started with, let's say, uranium and you may end up with strontium or something. But the fact here is that the atomic number of the reactants will be equal to the atomic number of the product. That means the atomic number is preserved. In other words, the number of nucleons is not destroyed. And this reaction requires huge amount of energy. In fact, if I compare it with the chemical change, then there is somewhere around 10 to the power 6 times more need of energy as compared to chemical change. Now it is written also, a nuclear change requires nearly 10 to the power 6 times more energy compared to a chemical change. Now in a nuclear reaction, the atomic number and the mass number remain conserved, as I mentioned. Now If I talk about the nucleus, then the size of nucleus is even smaller, that is of the order of 10 to the power minus 15 to 10 to the power minus 14 meter. Now here I will give you an analogy to make you understand the size of nucleus and the size of atom. So consider that you have a football and that football is the nucleus. Then the complete size of the stadium will be the size of an atom. So all the mass, just imagine, all the mass of the atom is concentrated, or you can say all the mass of the stadium. In that analogy that I have given just now, I can say that all the mass of the stadium is concentrated in the football. So football is the nucleus and the stadium is the atom. So just imagine how much empty space we have within an atom, and that was something which was observed by Rutherford as well in the alpha particle scattering experiment. Now we will understand some technical terms related to an atom, that is at mass number, atomic number, the mass of an atom, and whether the atoms are electrically neutral and how they manage to do so. Now first is mass number. So if I talk about mass number, it tells us, actually you see, at a very basic level, at a very granular level, what is mass number? So mass number means the number of particles which contribute towards the mass of an atom, and we know that these are nucleons, that is neutron and proton. So mass number is nothing but the total number of neutrons and protons present in an atom. Next is atomic number. Atomic number is the number of protons present in the nucleus of an atom. Now you might wonder that in fact if an atom is electrically neutral, then it means that the number of protons and the number of electrons must be equal in an atom. So for defining atomic number, why don't we say it like this, that the number of electrons present in an atom is called the atomic number? Well, there is a catch here, and I want you guys to comment in the comment section that why we do not use number of electrons in defining the atomic number. Next, the mass of an atom. So mass of an atom is slightly different from the mass number. Mass of an atom is defined as the sum of the masses, not the number of neutrons and protons, but the sum of the masses of neutrons and protons present in an atom. Now, the symbol used for an atom of an element is XAZ, and it is very simple. If let us say I am talking about carbon, let us say that the mass number of carbon is 14 and the atomic number Z is 6, then I will write it as C146. Mass number is always written in the superscript and atomic number is written in the subscript. Next, we will understand isotopes. Now, what are isotopes? If I talk about isotopes, then isotopes are those, you can say, substance which have same number of protons but different number of neutrons. In other words, they have same atomic number but different mass number. So in a way you can say, we also know, like in periodic properties of elements, we have studied that the properties of elements are actually the periodic function of their atomic number, not atomic masses. So it means that if I am talking about atomic number, like atomic number being same, that is number of protons and number of electrons being same, then it means that it is the same element. For example, it is hydrogen. Now in hydrogen itself, there might be scenarios like some atoms of hydrogen might have 0 neutrons, they might have 1 neutron, they might have 2 neutrons as well. Okay, now depending on this, there are slight differences in the physical properties of these isotopes. However, their chemical properties remain the same, stay the same. Now here some examples are given, like first one is hydrogen. Hydrogen has 3 isotopes. First is H1 protium, which is the most common. Then we have deuterium, which has 1 proton and 1 neutron. Then we have tritium, which has 1 proton and 2 neutrons. And tritium is the rarest of isotopes possible for hydrogen. Next we have carbon. Carbon again has 3 isotopes. C12, the most common, C13, the intermediate one you can say, and C14, which is rare. In fact, it is found somewhere around 1 to 3% only. If you have, let's say, a carbon, certain mass of carbon, then out of that, only 3% of carbon will be C14 carbon. And this carbon is actually radioactive in nature. We will explore this in the upcoming slides. Next we have chlorine. Chlorine has 2 isotopes, that is Cl35 and Cl37. Now, I have a question here for you guys. Again, you guys have to answer it in the comment section. There is one element which has the highest number of isotopes possible, okay, out of all the elements that we know. And let me give you one hint, it has a total of 10 isotopes. Can you name that element in the comment section? Please do it. Now, let us move forward. Then, if we talk about isotopes, then isotopes can further be divided into two categories, stable and unstable or radioactive isotopes. When we talk about stable isotopes, then in these isotopes, the number of neutrons is somewhat, you can say approximately equal to the number of protons. Then, such isotopes are called stable and they do not show radioactivity. But for some isotopes of an element, you will find that they have abnormally high number of neutrons compared to protons. For example, if I take the previous one, that is C14, then it means it has 6 protons and 8 neutrons. Now it might seem that okay, here we have only 2 neutrons in excess. So how is it possible that C14 is showing radioactivity? Now for this you need to check the percentage increase or the percentage by which the number of protons or the number of neutrons, the number of neutrons is higher in this case compared to the number of protons. So if you take the percentage, you will find that this specific isotope has 33% more neutrons compared to its protons, and that is why this isotope C14 shows radioactivity. And always remember, if an isotope is unstable, then it will show radioactivity. Now next is isobars. Now isobars are those substances which have same mass number but different atomic number. Now here, since the atomic numbers are different, then the elements have different chemical properties also. But the catch here is that they have same mass number. Now that means the number of nucleons is the same. Now since the atomic number is different, so let us say if I go by the example of Na and Mg here. So Na, the mass number is given to us as 23, and for Mg also it is 23. For Na the atomic number is 11, for Mg the atomic number is 12. So if I try to find out the number of protons and neutrons for Na and Mg, so for Na, let us say this is proton, this is neutron. So for Na the number of protons will be 11 and number of neutrons will be 12. But for Mg, the number of protons will be 12 but the number of neutrons will be 11. Now when you take the sum, you will find that the total number of nucleons stays the same. Now since the total number of nucleons are same, hence these two elements, that is Na and Mg, will be called isobars. Now a catch here is that if you look carefully to Na and Mg, then what is happening? Number of protons of Na is same as the number of neutrons of Mg, and the number of protons of Mg is same as the number of neutrons of Na. When we see such transition, that the number of protons of one element becomes the number of neutron of another, and the number of neutron of that element becomes the number of proton of the first, then we say that such isobars are mirror isobars. Okay, now I'll give you a task once again, that you have to identify more mirror isobars from the periodic table. Now another example of isobar is given here, that is carbon 14 and nitrogen 14. Now let us understand isotones. Now isotones is basically a property specific to nucleus. Now within a nucleus, we know that we have neutrons and protons. Now we say that two different elements are isotones if the number of protons are different but the number of neutrons are exactly the same. Now here we have an example, that is Na23 and Mg24. In fact, don't get confused, in the previous slide we used Mg23, here we have Mg24. So you can say that Mg23 and Mg24 are isotopes. But in this case, if I take Na, then its number of nucleons is, you can say N plus P is how much? It is 23. That means I have 11 protons and 12 neutrons. And if I talk about Mg, N plus P is 24 and I have 12 protons and 12 neutrons. If you'll see carefully, then the number of neutrons is same in both Mg and in both Na and Mg24 isotope. So we say that Mg24 and Na23 are isotones. Another example of isotone is given here, that is potassium 39 and calcium 40. Now let's talk about radioactivity. Some examples of radioactive substance are given here, such as uranium, radium, polonium, thorium, then we have plutonium. In fact, any element which has its atomic number greater than 82 will show radioactivity. Either some of their isotopes will show their radioactivity, or all the isotopes that we know for a given element is going to show radioactivity. Now what is radioactivity? So you see what happens, heavier elements, and in fact in case of lighter elements also, we have this property, like in case of carbon, potassium, cobalt also, all these elements show radioactivity. But let's talk about heavier elements, for example. So in case of heavier elements, what happens, that the number of neutrons is much more than the number of protons in their nucleus. So due to this, these atoms, the atoms of these elements actually become highly unstable, and what they do, they emit spontaneous radiations, they disintegrate. So while disintegrating, the nucleus of these elements actually emit some radiation. These radiation can be alpha, beta or gamma radiation. Okay, so that phenomena is called radioactivity. Now if I talk about the history of radioactivity in brief, then Henry Becquerel was the first one to discover these radiations. He found out that there are some elements which emit some kind of radiation on their own. And those radiations initially, since it was found by Henry Becquerel, those radiations were also called Becquerel rays initially. But later on, Ernest Rutherford conducted multiple experiments on these rays, and he found out that these rays are not a single beam of ray, rather they consist of 3 different components. And these components are alpha rays, which are positively charged, beta rays, which are negatively charged, and gamma rays, which are uncharged rays. We will explore these 3 rays in detail in the upcoming slides. So let us move forward. Now, if we talk about radioactivity, then again it is a property of nucleus, as I mentioned, that it has to do something with the number of protons and neutrons. Either the number of protons is going to change, or if it does not change, then at least the nucleus will be in some kind of excited state. That means the nucleus contains excess of energy which it needs to radiate, and that energy is radiated in the form of either alpha or beta and gamma radiation. Now, here one important thing to understand is that we have written here alpha or beta and gamma radiation. Let us read the statement first. It says, radioactivity is the process of spontaneous emissions of alpha or beta and gamma radiations from the nucleus of atoms during their decay. So decay means disintegration. Okay. Now, we are saying that alpha or beta and gamma. So what does it mean? It means that if I'm talking about at the atomic level, let us say that I consider an atom of uranium, then if this atom disintegrates, then definitely it is going to emit gamma radiation, because the energy of the nucleus is very high. The nucleus is in excited state. But when it comes to alpha or beta, which of these two will be emitted, then any one of these is going to be emitted. Both alpha and beta will not be emitted from a single atom. Always remember it. So if an atom disintegrates, it is possible that alpha emission happens and along with it gamma emission happens. If let's say another atom disintegrates, then in that case it is possible that beta emission happens along with gamma emission. But for any given atom, alpha and beta emissions are not going to happen simultaneously. These will happen in different atoms. Some atoms may give out alpha rays, some atoms may give out beta rays, but a single atom will never give out both alpha and beta rays. And gamma is common to both. No matter what happens, even if there is alpha emission, gamma radiation will be given out. Even if it is beta ray emission, gamma radiation will be given out simultaneously from the same atom. Now, radioactive decay, if we talk about the procedure, then that let's say if let's say we are interested in finding out if let's say that one atom has disintegrated. So is there any way to find out which atom will disintegrate next? Well, precisely speaking, there is no way to find this out, and the same has been mentioned here, that radioactive decay is a random phenomena. Random phenomenon means that we cannot predict that which atom of a given element is going to disintegrate next. Let us move forward. Now let us understand these emissions, alpha, beta and gamma emissions independently, one by one. Now you see, I mentioned when I started radioactivity that Henry Becquerel found out that okay, there are some kind of emissions from certain kind of elements. Those elements were called radioactive. But it was Ernest Rutherford who first identified, or who was first able to establish, that these rays are not single rays, or they do not comprise of only one kind of particles, okay, or they are not a unique radiation. These radiation actually comprises of 3 different kinds of components, and these components are alpha particle, beta particle and gamma particles. So how he was able to establish it? Basically he conducted an experiment, and in that experiment he subjected the Becquerel rays through magnetic field as well as electric field, and what he found as a result was astounding. He found that some part of the radiation got deflected towards the north pole when it was subjected to magnetic field, of course, and some of the part of the radiation got deflected towards the south pole. But there was one part of the radiation which went undeviated throughout the magnetic field. Then he repeated the same experiment in the electric field. He found that some of the part got deflected towards the negative terminal and some part of the radiation got deflected towards the positive terminal. Again, in this case, what he found, that there is one part of the radiation which does not get deflected, which did not get deflected in any direction. It passed straight away through the electric field also. So what he did, he said that okay, there is one part of the radiation which is going towards the negative terminal. So that part of the radiation was called alpha ray or alpha particles. Then there was one part which got deflected towards the positive terminal. That was called beta rays. And then there was one part which went undeviated, and that part was called gamma rays. Now, let us understand few more things about these radiations. So here, if you will see the deviations in the particles, that is alpha and beta. Now we know that this is alpha and this is beta. So let us understand one thing here. If you see the deviation in alpha particles, then in alpha particle the deviation is less, and in beta particles the deviation is large. So naturally it comes to our mind that alpha particles are heavy and beta particles are light. Upon further investigation, it was found out that these alpha particles are actually comprised of 2 protons and 2 neutrons. And from our understanding of periodic table, we know that there is one element which consists of 2 protons and 2 neutrons, that is helium. But surprisingly, these alpha particles do not have any electrons. These are positively charged. In fact, these are doubly charged helium atoms, and the charge is actually positive. So this alpha rays are nothing but He2+, and these are called doubly charged helium atoms. Okay. Now, if we talk about these beta particles, then beta particles, upon experimentation, it was found out that these are nothing but high energy electrons. Now, we know that electrons are lighter compared to alpha particles. Naturally, it has to be lighter because electrons have mass negligible when compared to even a single proton or neutron. But here we have in total 4 nucleons, that is 2 protons and 2 neutrons. So these alpha beta particles have to be lightest, and that is why the deflection is huge in case of beta particles. Now, these beta particles, and hence it was established that these beta particles are nothing but electrons. When it came to the part of the ray which went undeviated, it was found out that these are nothing but high energy, very high energy electromagnetic radiation, and these radiations were called gamma rays. Now, let us move forward. Now, let us understand the properties of alpha, beta and gamma rays or gamma particles one by one. So here, if we talk about the nature, which we already saw in the previous slides, the alpha particles are positively charged particles, or you can say these are helium nucleus without any electrons. Next, if we talk about the speed is slightly less than the speed of light, and it is nearly 10 to the power 7 meter per second, which is again very large, but compared to the speed of light, it is much smaller. If we talk about the rest mass, then rest mass of alpha particle is 4 times the mass of a proton, because we know that the alpha particle is nothing but 2 proton plus 2 neutron, and proton and neutron have approximately equal masses, and that is why it is simply written as 4 times the mass of a proton, and it comes out to be 6.68 into 10 to the power minus 27 kg. Next we have charge. Now since we have 2 protons and no electrons, so the charge on alpha particle is naturally going to be the charge of 2 protons. One proton has a charge of 1.6 into 10 to the power minus 19 coulomb. So since we have 2 protons, the charge will be 3.2 into 10 to the power minus 19 coulomb. Next we have specific charge. Now specific charge is slightly different from the normal charge. If we are saying only charge, then it means we are talking about charge on one ion or atom. When we talk about specific charge, it actually means that we are talking about the charge on 1 kg of anything. In this case we have alpha particle, so we are talking about charge on 1 kg of alpha particle, and that charge is 4.79 into 10 to the power minus 7 coulomb per kg, and that is why you have here per kg, that for every kg of alpha particle what is the charge that is being carried. Next, wavelength. Since these are particles, not radiation, so there is no concept of wavelength here, and wavelength is nothing. Next, effect of electric and magnetic field. We have already studied in the previous slides that alpha particles in the presence of magnetic field get deflected towards the north pole, and in the presence of electric field they get deflected towards the negative terminal. Now let us move towards beta particles. So if we talk about the nature of beta particles, then these are negatively charged particles. To be precise, these are high energy electrons, nothing else. If we talk about the speed is very close to light, and it is 2.7 into 10 to the power 8 meter per second. Rest mass, it has to be the mass of electron, that is 9.1 into 10 to the power minus 31 kg, because no matter, even if they are excited, high energy electrons, but they are electrons, right? So their mass is not going to change. Next we have charge. So charge on 1 electron will be the charge of one beta particle, that is minus 1.6 into 10 to the power minus 19 coulomb. And next we have specific charge. For 1 kg of beta particle, what is the charge that will be carried? It is 1.76 into 10 to the power 11 coulomb per kg. Wavelength, since beta particle is particle, in fact these are not radiations, or you can say waves, so wavelength is nothing. Next, effect of electric and magnetic field. We saw it in the previous slides as well, that in case of magnetic field, beta particles gets deflected towards south pole, and in case of electric field they get deflected towards the positive terminal. Now let us see gamma emissions or gamma rays. So if we talk about the nature, these are high energy electromagnetic radiation. If we talk about speed, so these are electromagnetic waves, right? So any electromagnetic wave actually travels with the speed of light. So the speed of the gamma ray is also 3 into 10 to the power 8 meter per second, that is the speed of light. Next, rest mass, since it is a radiation, it is a wave, it is not a particle, so rest mass is nothing. It will have no rest mass. If we talk about charge, these are uncharged particles, and hence the specific charge is also going to be nothing. Next, let us understand wavelength. So wavelength is of the range from 10 to the power minus 4 nanometer to 10 to the power minus 13 nanometer, and these are very high energy radiations. They can even penetrate our body completely. Okay, they can even penetrate the whole surface of Earth as well. Now, effect of electric and magnetic field, we have already seen that gamma particles or gamma rays do not get deflected either in the presence of magnetic or electric field. So they are unaffected precisely. Now we will understand that what happens inside the nucleus of a radioactive substance during radioactive decay. Now this is something which I have already explained, that during a radioactive decay of a radioactive substance, either alpha, beta and gamma rays are emitted. Alpha and gamma or beta and gamma will be emitted. And why these emissions happen in the first place? So you see, the objective of these elements is to attain a stable nucleus. If the nucleus is too large, then again it is unstable. If the nucleus is too small, or you can say the number of neutrons, specifically the number of neutrons is too huge inside the nucleus, no matter the element is heavier or the element is lighter, it will undergo a radioactive decay, so that on an average the number of neutrons and the number of protons become approximately equal within the nucleus, and in order to do so they undergo radioactive decay. Now you see, one of the most stable elements that we know of is actually iron. And in fact, in one way or another, in fact, it is something which is being explored in astronomical sciences also right now. And there is one anomaly behavior that is shown by iron, which I will explain in this in the class itself, related to iron. So what is the thing here is that iron is considered one of the most stable elements. And what actually these elements do, if they are too heavy, if they are too light, they actually try to become iron. They actually want that their nucleus should be same as that of iron. And it is something which is evident in our universe also. We know, in fact, we all know that the most abundant element in our universe is hydrogen. And then we can create a hierarchy. So what happened? Astronomers or astrophysicists, they actually tried to find out how much of these different elements that we know of actually exist in the universe. So according to their prediction, let us say, I don't remember the numbers exactly, but let us say that they felt that iron should be somewhere around 2 kg. For example, again, I don't know the exact number. I just want to show the anomalic behavior of iron. And that actually validates the statement that I made, that iron is one of the most stable nucleus. Iron has one of the most stable nucleus, and no matter whether an element is heavy or light, they will try to have a nucleus similar to that of iron. So it was assumed that iron in our universe should be somewhere around 2 kg, hypothetically. But when they actually look into the universe, what they found was completely astounding. They found abnormally high levels of hydrogen in our universe. Abnormally high. It is still less than hydrogen and helium, of course, because these are the most abundant elements in our universe. They form stars, they are present in the nebulae gases everywhere. But still, iron should have been, the mass of iron should have been somewhere around 2 kg, hypothetically, but it was found much more than that. It was, let's say, somewhere around 6 or 7 kg. So why iron is present in so much abundance in our universe? So the answer is simple. If it is a lighter element, it wants to become iron. If it is a heavier element, it wants to disintegrate and become iron. And that is why iron is abnormally high in our universe. So now let us move towards our, let us get back to our discussion and let's see what is the next point. So alpha and beta emissions lead to a change in the number of protons and neutrons. So whenever there is alpha emission or beta emission, it will lead to a change in either the number of protons or the number of neutrons or both of them. In case of alpha, the number of neutrons as well as protons change. In case of beta emission, only the number of, again, the number of neutrons and the number of protons change. But if I talk about the number of nucleons, then in case of alpha emission, the number of nucleons will change by 4 because 2 neutrons and 2 protons are lost. In case of beta emission, what actually happens is that 1 neutron gets converted into a proton. So although the number of neutrons and protons are changing within the nucleus, but the number of nucleons remains same. And in case of gamma emission, there is no change in nothing. Like neither the atomic mass will change, neither the atomic number will change. What is, when we see gamma emission, let us say there is a nucleus which has very high energy, abnormally high energy. So what this nucleus will do? It will lose its energy, and this energy is lost in the form of high energy gamma emissions. Okay, so now let's talk about these changes. Like first we will discuss alpha emission. So what actually happens in alpha emission? So alpha emission is very simple. In case of alpha emission, we have a nucleus. Let's say here we have a nucleus X, which has a mass number A and the atomic number Z. Now in this case, in alpha emission, what happens? The atom actually disintegrates and it actually forms a, you can say, forms another element. It actually gets converted into another atom of another element, that is, let's say Y, and it releases a helium nucleus, which has a mass number of 4 and atomic number of 2. Now what will happen? You see, helium is what? Helium is 2 proton plus 2 neutron. Okay, when we talk about the atomic number, we have studied that atomic number is nothing but the number of protons present in the nucleus. So here we have lost 2 protons to produce helium ion, right? So what will happen? My atomic number will get decreased by 2. But when it comes to mass number is the sum of the number of protons and the number of neutrons. And how many protons and neutrons in total we have lost? We have lost 4. And that is why the mass number gets reduced by 4 and we get a completely different element. Okay, so for example, if I take an example of uranium, so in case of uranium, uranium disintegrates and of course it gives out helium ions. Along with it, the new element formed is thorium, okay, which has an atomic mass 4 less than that of uranium. Now let's talk about beta emissions. So in case of beta emission, you see what happens is that there is no change in the mass number. Why? Because I told you at the start of this change within the nucleus, at the start of this discussion, that in case of beta emission, we have a neutron getting converted into a proton. Okay. So due to this, what happens? The number of nucleons is not going to change. So let us say initially there were 20 neutrons and 20 protons. Hypothetically, again, in this case, this nucleus will not show radioactivity because the number of protons and neutrons are equal. But again, I'm just taking an example, or let's make it different. Let's say it is 30. Okay, now let us say one of the neutrons gets converted into protons. So what will happen? Now I end up with 29 neutrons and 21 protons. So what about the mass number? If I talk about the mass number is simply the sum of neutrons, number of neutrons and protons. Here it is 50. Here also it stays 50. But what happens to the atomic number? Previously, I had an atom which had an atomic number of 20, and now I have another atom which has an atomic number of 21. So atomic number changes. That means the element has now changed. The atom has changed in its chemical properties also, because now we have completely different element. Now since it has one extra proton. Now one more thing you need to understand here is that we also discussed isotones in this chapter, right? And in isotones we studied that if the mass number is same, but the number of protons are different, isobars. We have studied that we have isobars, right? So if the mass number is same, but the number of protons in the nucleus is different, then we call them isobar. So in case of beta emission, we get isobars. So here you see, mass number is same for both of them, but atomic number is different. And that is why P and Q are also isobars. Now, what happens here? This equation is actually important. So what is happening here? So you see, we know that in beta emission, what happens? One proton is being created, but beta are negatively charged. So from where this negative charged radiation comes out. So you see, neutron is a neutral particle. If I am producing a positively charged particle out of a neutral particle, that means neutron, then I need to have an electron also. And we know that electrons cannot stay in the nucleus. It has to be either in the orbital or outside the nucleus. Okay. So proton stays in the nucleus, but the moment this neutron gets converted into proton, this electron gets ejected almost instantaneously from the nucleus at very high speed. And this ejection of electron is seen by us in the way of beta emission. Now, again, you will study about this in higher classes, but there is one more thing that is included in this equation, which is anti-neutrino, which is also, you can say, produced in this decomposition. Okay. Now we will understand gamma emission. In case of gamma emission, there is no emission of the alpha or beta particles. In fact, there is no change in the number of nucleons present in an atom. And this gamma emission can come out of the parent, or you can say the daughter atom. Now the thing here is that whenever for a radioactive substance or for a radioactive atom, during the radioactive decay, it might contain excess of energy. The nucleus of that atom might contain excess of energy, and that atom can be the parent atom which has decayed, or the daughter atom which has been created after the decay. Now due to this excess energy present in the atom, it emits a radiation, high energy electromagnetic radiation, which comes out in the form of gamma radiation. And that is why for gamma radiation, there is no change in the mass number or the atomic number of the radioactive atom. And this relationship actually signifies that, and you can see here clearly that we have an atom which is in excited state. This star sign actually denotes the excitation of the nucleus of the atom. Upon releasing the energy which comes out in the form of gamma radiation, which is a high energy electromagnetic radiation, the excitation, the energy is lost and the atom becomes neutral. Next, we are going to understand radioisotopes. Now you see, if we are talking about radioactive substances, then I have told you also in the previous slides that if an atom has an atomic number, or let's say if an element has an atomic number greater than 82, it will show radioactivity. But there are certain elements which actually show radioactivity, but their atomic number is less than 82. In fact, for those elements, I would say that there are certain isotopes which show radioactivity. For example, if I take carbon, then carbon has 3 isotopes, C12, C13 and C14. Now out of these 3, C14 shows radioactivity. In the same way, we have potassium which shows radioactivity. One of the isotopes of potassium shows radioactivity. Then we have cobalt which shows radioactivity. Okay, so now here you see certain examples are also given: cobalt, carbon 14, potassium 40 and phosphorus 32. These are the isotopes of these elements which show radioactivity, and these are then hence called radioisotopes. Now these radioisotopes are actually very useful. They find their application in medicine, in science and in industry. And now one by one we will see its uses, some of the uses in the medicine, in scientific research and in industrial usage. Now first we will understand its medical use. So in treatment of diseases such as leukemia and cancer using radiotherapy. In this case what happens, we use radioactive isotopes which are also called tracers, for example carbon 14. And using these tracers, or cobalt 60, sorry, in case of radiotherapy, cobalt 60 isotope is used. So this cobalt 60 is actually used in treatment of, in killing actually the cancer cells. And you might have seen those cancer patients also, their all the hair are gone and things like that happen. So it happens because of the effects, side effects of those radioactive substances. Next, it helps in the diagnosis of certain diseases and in radiocardiology, again using tracers. So tracers are a special class of radioactive isotopes which are simply, you can say, cobalt 60 or carbon 14. These are called tracers actually. Okay. In medical science. Now, what is radiocardiology? So in radiocardiology, what happens? As the name suggests, it's cardiology. So I need to understand our circulatory system. So for understanding the circulatory system, what we do, we inject these radioisotopes, or in other words, these tracers, into our veins or into our blood vessels. And these are then analyzed in order to find out how the circulatory system is performing for a human body. Next, gamma rays from radioisotopes are used to sterilize various medical equipments. Okay, so again, gamma rays, we know that it is high energy electromagnetic radiation. And these radiations are sufficient to kill microorganisms or germs present on the surface of any kind of medical equipments, be it bandage, be it the scissors, be it the blades that are used to cut the body parts. Everything can be sterilized using gamma rays. Next, we will understand the scientific use. So if we talk about scientific use, it has multiple actually. Alpha particles, which is doubly charged helium ions, from radioisotopes are used as projectiles for nuclear reactions. These alpha particles are actually bombarded into the atoms, and then nuclear reactions are conducted, which are then studied to understand the nature of an atom. Okay, then radioactive tracers are used in agricultural science to study the growth of plants by using a particular chemical manure. We need to understand, like if you want to increase the efficiency of a manure or a fertilizer, then we need to understand how a fertilizer helps in the growth of plants, which all parts of the plants are most affected by a given fertilizer. So in order to assess that, we use radioactive tracers. Then, to identify the age of excavated material of archaeological importance. We know this phenomena, it is called carbon dating. So in this, what happens, we use C14 isotope to understand how old a given archaeological artifact is. Now let us understand the industrial use. So in industry, radioisotopes are used as fuel for the atomic energy reactors, very common. You can say nuclear power plants, their radioactive isotopes are used. Then these are also used by engineers to avoid accumulation of charge on moving parts of machine due to friction. Now you see, we have studied in electrostatic force that if two surfaces are rubbed, of course there are certain criteria like which all two surfaces will be rubbed, but generally what happens when two surfaces are rubbed, then due to friction, charges accumulate on the surfaces of the objects which are rubbed together. So these charges can be problematic for the machines which are being used by engineers, specifically when these machines are of great scientific importance and they are highly sensitive, let us say. So in that case, accumulation of charge is something which cannot be afforded, okay, which is not affordable, or which cannot be tolerated in fact. So in this case, what happens, the moving parts of the machines are coated with these radioactive substances. Now what does these radioactive substances do? They actually charge up the surrounding environment. in the with the charge which is opposite to the charge developed in the machine, which then neutralizes any charge which is developed in the moving parts of the machine. Next, these are used to make luminescent signs due to the ionizing effect of these radiations. Luminescent sign you might have seen when you're walking on the road, if you are traveling on a vehicle and with your headlights on in the evening, then you might have seen along the road at the corners there are some red lights which appear at the sides at regular intervals. So these red lights are actually not red lights. There is no light inside it. These are certain materials. There are certain materials put into it, and these materials are actually radioactive, which are put into it, which upon when the lights fall onto them, they give out certain kind of luminescence, and that luminescence is actually perceived by our eyes. So it finds its application there also. Then they are used to control the thickness of paper, plastic or metal sheets during their manufacture. And specifically when these metal sheets or plastic sheets or paper sheets are being manufactured for very sensitive purposes. So in that case we require, in fact it becomes important that these thickness of the paper or thickness of the metal sheet is completely uniform, and these radioactive elements actually help us to do so. And how they help us? So we know that alpha, beta and gamma particles have different penetration power. Of all these three, alpha particle has lowest penetration power, beta has slightly more penetration power compared to alpha particles, and gamma emissions have the highest penetration power. So depending on how much thickness we need, we use different radiations, different emissions, either alpha, beta or gamma, so as to ensure that the thickness is uniform. Next, let us understand sources of harmful radiations. So you see, radiations can be harmful. It can create great biological problems for us, and we first need to understand what are the sources of these harmful radiations. So first is radioactive fallout, and this can happen due to multiple reasons. Okay, so first and most simple reason is that we are now heavily dependent on nuclear energy for electricity generation. So if we are producing electricity using nuclear substance, using radioactive substance, then it means we are producing waste products which are also radioactive. And in the past, there have been accidents in these nuclear reactors, and three most notable ones actually happened in USA in 1979, Ukraine in 1986, and Japan in 2011. The most recent one being in Japan. There was an earthquake in Japan in 2011, and there was a reactor in Fukushima, and that earthquake was so violent that this reactor got destroyed, and it created a hell lot of problems for the people who lived in Japan actually. Then Ukraine, this is the most disastrous nuclear, you can say this is the most dangerous nuclear disaster ever to happen on Earth. Apart from the nuclear weapons, of course, these are nuclear accidents, you can say, the most disastrous nuclear accident. So you might have heard the name Chernobyl. In Ukraine, there is a place named Chernobyl. And in 1986, Ukraine was actually part of USSR. Now, in 1999, I think, or 91, sorry, USSR dissolved and Russia came into existence. Along with it, some smaller countries were formed. One of them was Ukraine. So Chernobyl now is in Ukraine. And in Chernobyl, in 1986, there was a huge nuclear blast in one of the nuclear reactors, which was situated in Chernobyl. And due to this region, what happened? Now that place cannot be inhabited for, let's say, on a safer side, even if I say, then for the next at least 50,000 years, that place cannot be inhabited by any life form. So that's the problem. That's the level of difficulties that these nuclear radioactive substances can actually create. Next, we have nuclear waste. So you see, whenever there is a nuclear reaction, we are left with nuclear wastes, and those nuclear wastes are also radioactive. If they are not disposed properly, then it will create problems for our environment as well as all the life forms living in that environment. And that is why handling of nuclear wastes is very important in case of radioactive substances. Next, cosmic radiation and X-ray. You see, we are not always safe. In fact, if I talk about sun, it emits a lot of cosmic radiation which comes in the form of gamma rays and X-rays, and these can be dangerous for our body. But thankfully, for Earth, the Earth's magnetic field, we know that Earth behaves as a big magnet, right? And it has its own poles, magnetic poles, and that actually creates a magnetic field around the Earth's atmosphere. So this magnetic field actually protects us from these cosmic radiation and X-rays. In fact, not all the rays or not all the radioactive emissions are driven out by the magnetic field. There is one part of the emission of the solar radiation or cosmic radiation, which actually penetrates the atmosphere, even it crosses the magnetic field. Now it is easy to understand. We know that radioactive emissions have three components: alpha, beta and gamma component, right? And in magnetic field we know that alpha and beta component easily get deflected, but gamma component remains unaffected. So although alpha and beta components get deflected from these cosmic radiation, but the gamma radiation comes straight to us, okay, and that can create problems if we are exposed for a longer period of time. Now, harmful effects of radiation. Now, what are the problems that are caused by radiation? So basically, there can be three types of problems if we are talking about human beings. Some can be short-term recoverable problems, then long-term irrecoverable problems, and there can be some genetic impact as well. If we are talking about these two impacts, then these are evident on the individual itself. Let us say I get exposed to huge levels of, let's say, these radioactive radiations. Then these two things are something which will show effect immediately on me. But when I talk about genetic effects, let's say there is some genetic impact of this radiation on me, then it will not get reflected upon me, but rather it will get reflected upon the offspring from me. Okay, so that's the thing that happens. So genetic effects does not show up immediately because it has changed my DNA, my genes, which will be shown, and its effect will be shown in my offspring, not me. But if the effects are of these two nature, like long-term recoverable or irrecoverable, then it will be shown on me. Now, the exposure of pregnant women to X-rays over a long period of time increases the risk of cancer by 40%, tumor and nervous system issues by 50%, and leukemia by 70% for the child that is present in the womb of the pregnant woman. And that is very, very dangerous. So you can understand how dangerous these X-rays are. But remain assured, you need to get exposed heavily for the X-rays. So if you are going to have an X-ray of your hand for, let's say, a fracture, to check for a fracture, then that is not going to create a problem. You have to get exposed for a very long period of time, which is generally not the case in case of when we are talking about the medical use of X-rays. However, we should be aware that X-rays can be dangerous, and especially for pregnant women. Now, exposure to gamma rays destroy the cells and affects gastrointestinal tract, along with causing harm to DNA and RNA. I think about DNA and RNA I have already told, because these are actually reflected in the form of genetic effects, like they can alter, the gamma radiations can actually alter. These are high energy radiations, right? And they can interact with the molecules present in our DNA, and they can alter the types of bonds that actually exist between different DNA molecules, between different molecules of a DNA, sorry. Okay, and that can actually lead to genetical changes. It can also alter cells. It can lead to increase in the number of cancer cells. It can affect our gastrointestinal tract, that means our whole digestive tract. It can affect different parts of the tract in a different manner. And like mostly in case of cells, the type of cells which are mostly affected are blood cells. Okay, so now let us move forward and let us understand background radiations. So you see, no matter what happens, no matter how isolated environment I am able to create, but there will still be some background radiations, and the source of these background radiations can be internal as well as external. Now, internal sources of radiations are from within our body. So you see, in our body we have carbon and we have potassium, and in very, very small amount, carbon-14 and potassium-40 are present in our body itself, and those emit radiations. However, the level of radiations, the extent to which these radiations can affect our body is very, very low, and it does not create any serious problems for us. Then we have external sources. External sources, one is the solar, the cosmic radiation that we receive, and then there are substances around us which can emit radiations. Okay. Like radium, for example. Radium was used for quite some time in the past as a fluorescent material, but later on it was realized that it is radioactive and it can create problems for us if exposed to huge amount of radioactive, or you can say to huge amount of radium. So these are external sources. However, if we are talking about these background radiations, then these do not pose very serious problems for us, because these are way below the level of exposure that is needed to impact our body. So with this, we conclude our discussion on radioactivity. I hope you guys were able to understand the concepts that we have studied today. If you have any queries, any doubts, then please mention it in the comment section. We will answer it. Also, if you enjoyed the video, then please do like, comment and subscribe to our channel, Midha Guru.